The concept of a data center on the moon might sound like science fiction, but its feasibility is rapidly becoming a topic of serious engineering discussion. We are exploring whether this ambitious endeavor is mere fantasy or a tangible near-future reality. Our goal is to move beyond speculation, sketching a plausible design for a lunar data center that could be operational by the 2030s. This involves dissecting the technical challenges and proposing innovative solutions. A primary driver for lunar data centers is latency reduction. The inherent one-way communication delay between Earth and the Moon, approximately 1.3 seconds, severely limits real-time control and interactive operations. Local processing significantly mitigates this critical bottleneck. Furthermore, on-moon data preprocessing offers substantial bandwidth optimization. By filtering and compressing raw scientific data before transmission, we can drastically reduce the expensive downlink requirements to Earth. This makes lunar missions more efficient and cost-effective. Such a facility would also provide crucial autonomy and resilience for lunar operations. It could host local services for human crews and robotic assets, ensuring continuity even during communication outages with Earth. This local infrastructure is vital for sustained lunar presence. The lunar South Pole presents compelling advantages for a data center location. Its elevated ridges offer near-continuous sunlight, essential for solar power generation. Crucially, permanently shadowed regions, or PSRs, within the South Pole contain significant water ice deposits. However, the lunar environment is characterized by extreme temperature swings. Daytime temperatures can soar to 121 degrees Celsius, plummeting to -133 degrees Celsius during the lunar night. PSRs are even colder, dropping below -246 degrees Celsius. Intriguingly, natural thermal refuges exist in the form of lava tube pits. These subsurface structures maintain a remarkably stable temperature of approximately 17 degrees Celsius. Such natural shelters could offer significant advantages for thermal management. Power is arguably the most critical constraint for any lunar infrastructure, dictating the viability of compute, cooling, and communications. Reliable and abundant energy is the foundational requirement for a lunar data center. Polar solar power is a leading candidate, utilizing arrays deployed on continuously illuminated ridges. This approach necessitates robust energy storage systems, such as batteries or fuel cells, to sustain operations during periods of darkness. Fission surface power, or FSP, offers a powerful alternative. NASA and the Department of Energy are developing 40-kilowatt electric reactors, with 3 to 5 units potentially providing a stable 120 to 200 kilowatt electric baseload power. This ensures consistent energy availability regardless of solar conditions. A hybrid power system, combining solar, FSP, and energy storage, would offer optimal resilience. This configuration could handle peak loads and provide redundancy, ensuring uninterrupted operation even if one power source experiences an issue. Cooling a data center on the moon presents unique challenges due to the vacuum environment. Radiation to space becomes the primary heat rejection mechanism, necessitating large, high-emissivity radiators to dissipate waste heat effectively. The extreme day and night temperature swings demand a sophisticated two-mode thermal design. This system must efficiently manage heat rejection during scorching lunar days and prevent overcooling during frigid lunar nights. A robust loop architecture is essential for internal heat transfer. This involves cold plates directly contacting heat-generating components, pumped fluid loops to transport heat, and heat pipes for efficient thermal distribution to the deployable radiators. While PSRs offer easier cooling due to their extreme cold, they pose significant challenges for power generation and communications. Innovative solutions, such as fiber optic links extending from illuminated ridges to cool sinks within PSRs, might be necessary to leverage their thermal benefits. Lunar regolith, or moon dust, poses a significant hazard. It is highly abrasive, electrically clingy, and can foul connectors, coatings, and seals, leading to equipment degradation and failure. Mitigating its effects is paramount for reliability. One key mitigation strategy involves using pressurized, sealed racks. These could be housed within habitat modules or buried in subsurface vaults, creating a clean, controlled environment isolated from the pervasive dust. Employing dust-resistant components is also crucial. This includes specialized connectors designed to resist dust ingress, shielded cable trays to protect wiring, and airlock-style service hatches for maintenance access without contaminating the internal environment. Furthermore, electrostatic dust rejection technologies can be applied to critical surfaces. This involves using electric fields to actively repel dust particles from radiators and solar panels, maintaining their efficiency and longevity. Establishing a robust communications and navigation backbone is vital for lunar operations. Surface links, utilizing technologies like LTE/5G or Wi-Fi 6, will provide local connectivity for rovers, astronaut suits, and scientific instruments. Relay satellites, such as NASA's Lunar Communications and Navigation Network Services and ESA's Moonlight initiative, will provide commercial communications and precise positioning, navigation, and timing services. These satellites form the essential link to Earth and across the lunar surface. Interoperability will be achieved through LunaNet standards, enabling delay/disruption tolerant networking, or DTN, bundles. This architecture ensures data can be reliably transmitted and stored, even with intermittent or delayed connections. Finally, Earth gateways will bridge lunar data to terrestrial cloud infrastructure. The Deep Space Network, with its global array of antennas, will serve as a critical conduit for high-bandwidth data transfer between the Moon and Earth. A practical Phase 1 Lunar Edge data center would likely consist of 2 to 4 pressurized, ISRU-shielded rack pods. These modules would incorporate shock and vibration isolation to protect sensitive equipment during transit and deployment. The compute infrastructure would feature ruggedized edge servers equipped with accelerators for specialized processing tasks. Redundant boot images, error-correcting code memory, and mirrored NVMe storage would ensure high availability and data integrity. Networking within the data center would involve a local fiber ring for high-speed internal communication. Surface LTE/5G radios would provide wireless connectivity, complemented by microwave or optical links to external relay satellites. Operations would emphasize remote KVM for diagnostics, a DTN cache for data buffering, and Earth-Moon snapshot replication for disaster recovery. Fault-tolerant autonomous recovery mechanisms would be critical for self-healing capabilities. A lunar data center would primarily support key applications essential for sustained lunar presence. These include robotics and teleoperations, enabling real-time control of automated systems and remote manipulation. Science data preprocessing is another critical workload, allowing raw sensor data to be analyzed and compressed on-site before transmission. This reduces downlink requirements and accelerates scientific discovery. A habitat digital twin, a virtual replica of the lunar base, would enable predictive maintenance and operational optimization. Navigation and timing services would provide precise location and synchronization for all lunar assets. Finally, the data center would host crew tools, providing local computing power for mission planning, health monitoring, and educational resources, enhancing astronaut productivity and well-being. Designing a lunar data center requires a rigorous reality check, focusing on continuous power, dust mitigation, and thermal extremes from the outset. Fault recovery mechanisms must be integral to the design, not an afterthought. It is crucial to debunk common myths, such as the notion of free cooling from the lunar night. While cold, the vacuum environment makes heat rejection challenging, and active heating is often required to prevent components from freezing. Another myth is the near-term availability of helium-3 fusion power. While promising for the distant future, it is not a viable power source for a data center in the 2030s. Realistic power solutions must be prioritized. Considering the immense challenges and the current state of technology, the vision of hyperscale data centers on the Moon remains firmly in the realm of fantasy for the foreseeable future. The energy, cooling, and logistical demands are simply too great. However, a modest, rugged edge data center is a very different proposition. Such a facility, designed for specific mission-critical workloads, is entirely achievable by the late 2020s or early 2030s. This makes it a tangible near-future reality. The journey to establishing a lunar data center is complex but filled with incredible potential. It represents a critical step towards a sustainable human and robotic presence beyond Earth. Thank you for joining us on this exploration of lunar infrastructure. If you found this discussion insightful, please consider subscribing to Pulse Nucleum for more content on future technologies in space exploration.